The morning of March 20th, 1944, across a scarred field near the village of Colmar in Alsace, the rumble of tracked steel broke through the autumn mist. A column of 5-ton fuel trucks crawled along the narrow, muddy lane. At their head, a triumphant crew of the Panzer Lehr Regiment edged ahead in a captured American medium tank. The vehicle bore the bold white star of the United States Army on its turret side, but beneath it, the familiar German Balkenkreuz had been hastily painted. This was no trophy for the German propaganda ministry. It was a revelation. Not for what it could do, its 76-millimetre gun was outmatched, and its armour thinner than the German standard, but for how far it could go without breaking down. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. On that cold March morning, the engineers of the German Armour Development Division watched with a mix of wonder and dread as the tank covered 47 kilometres, without a single mechanical halt. Its tracks held in the deep mud. The cooling system resisted the freezing air. The engine, clutch and transmission functioned. Lieutenant Hans Müller, veteran of nearly 100 sorties in the Panther tank, looked on through his binoculars and muttered what he had never thought he would say. It simply works. What Müller and his fellow engineers were witnessing was the moment when one of the Wehrmacht's foundational beliefs collided with reality, the belief that German tanks were the pinnacle of fighting machines in Europe, that superior firepower and armour thickness dictated victory, and that reliability was a secondary concern. The reality exposed by this captured American machine, mass production discipline, industrial automotive engineering, and logistical robustness, could outmatch tactical or technical superiority. Question remained: could German industry admit this truth and change in time? To understand the magnitude of this pivot, one must first appreciate the mindset and the industrial military context that preceded it. By early 1944, the war in Europe had entered its most decisive phase. On the Eastern Front, the Red Army was preparing the summer offensive that would sweep the Germans from the Ukraine. On the Western Front, the Allies were gathering their strength in Britain, prepping for the cross-channel invasion. For the Wehrmacht's armoured crews, this meant one thing: increasing pressure, increasing range of operations, and increasing demands on their machines to perform reliably under punishing circumstances. Since the invasion of the Soviet Union in June of 1941, German armoured doctrine had championed the decisive strike. The heavy tank for breakthrough, the refined chassis for tactical flexibility, and the best crews backed by fuel and ammunition. The doctrine placed heavy weight on firepower and armour. The iconic Tiger I had a 90mm turret front. The Panther's gun could penetrate almost any Allied tank frontally at typical combat ranges. Vast resources went into these aspects. The German High Command believed that dominance in armour meant battlefield dominance, but the doctrine paid little heed to endurance, ease of maintenance, and the human factor of driving and sustaining a heavy armoured machine over long distances. Engineer workshops, mechanical supply units and fuel trains often lagged behind the spearhead, not because the crews were incompetent, but because the tanks themselves demanded frequent upkeep. In contrast, the American doctrine prioritized production speed, interchangeability of parts, and logistical simplicity. The widely produced M4 Sherman medium tank was less heavily armoured and carried a less powerful gun than the German heavy tanks, but it was simple to manufacture, simpler to maintain, easier for crews to learn, and it kept running. German tank engineers and logistics planners believed they could afford this trade-off. After all, they faced fewer opponents at any given time than the Allies, and their doctrine assumed shorter supply lines and greater operational initiative. Mechanical failures were tolerable when the enemy was weak and the campaign short, but as the war expanded, the assumption would be tested brutally. In the deserts of North Africa in 1942, German tank crews learned a harsh lesson. Heat, sand, and long supply chains placed extreme stress on mechanical systems. The Panther had yet to appear in numbers, and many Panzer III and IVs were forced to withdraw not due to enemy fire, but due to engine breakdowns, final drive failures, cooling system blockages, and exhausted crews. The retreat from Tunisia in May of 1943 exposed how mechanical fragility could end a campaign. German engineers took note, yet the deeper structural shift in industrial philosophy did not come until later. Back in Germany, armaments factories worked under severe constraints. Skilled labor shortages, Allied bombing, decimated transport infrastructure, and dwindling fuel stocks all conspired to limit what could be achieved. German designers still assumed that reinforcing firepower and armour would overcome these obstacles. But they were living in a shrinking archival world, while the Allies were living in a vast industrial ecosystem. Amid all this, the German tank crews continued to labour under the psychological weight of their own reputation. The Tiger driver who would fear no tank, the Panther crew who would strike before being struck. These images were everywhere, from newsreels to posters to self-help manuals issued to tank units in mid-1943. They reinforced the faith that German tanks were unstoppable, but that faith masked a critical vulnerability: the inability to sustain operations far from depot, with limited spares and overextended fuel lines. The captured Sherman in March of 1944 jolted this belief. The engineers who rode in it, those who observed it, and those who reported on it had to ask themselves the hardest question. If this inferior tank could perform dependably where ours faltered, what does that say about our doctrine, our industry, and our future? The answer would not be comfortable. In April of 1944, the captured Sherman, an M4A3 variant powered by a Ford GAA Veit engine, arrived at the German Army's testing grounds at Kummersdorf, 25 kilometers south of Berlin. It was assigned the experimental evaluation code Versuchsträger 503. Engineers from the Heereswaffenamt Army Ordnance Office and technical officers from Henschel and MAN gathered around the vehicle with a mix of skepticism and curiosity. They had tested Allied equipment before Grants, Stuarts, even early Churchills, but this was different. Those tanks had failed in ways that confirmed their prejudices. The Sherman did not. Under the low grey sky of a Brandenburg spring morning, the test began. A mechanic in grease-stained overalls turned the ignition key and pressed the starter. The Veit coughed once, then roared to life. It settled into a steady rhythm that astonished those accustomed to the more temperamental Maybach HL series engines. The Sherman idled evenly. The throttle response was smooth. Oberingenieur Karl-Heinz Bremer, a senior mechanical specialist from the Henschel plant at Kassel, recorded his first observation. Startverhalten, zuverlässig, sofortig, ohne besondere Vorbereitung. Starting behavior, reliable, immediate, without special preparation. In the German context, that was extraordinary. Maybach engines required meticulous preheating, careful fuel-air adjustments, and exacting throttle control during startup, especially in cold conditions. Tank crews were trained to listen for particular rattles, to adjust choke manually, to sense the right moment to engage the clutch. The Sherman asked for none of that. It behaved like a tractor, a vehicle meant for anyone to drive. The trials continued. The tank ran a 300-kilometre endurance loop along the rural Brandenburg roads, half paved, half unpaved. The engineers logged fuel consumption at approximately 1.5 litres per kilometre, consistent with American reports. But what startled them most was the consistent oil pressure and coolant temperature over long distances. The Tiger I's Maybach HL 230 engine, under similar load, would overheat within 50 to 80 kilometres, unless stopped for cooldowns. By the time the Sherman completed its third loop, it had covered nearly 900 kilometres without a single mechanical failure. Not a broken track link, not a seized bearing, not an oil leak that required attention. The German technicians, meticulous note-takers, began whispering among themselves that the numbers could not be right. One of them, a powertrain specialist named Ernst Fahl, later wrote in his notebook, which survived in the Bundesarchiv, "The Americans have built a tank that does not require an engineer's supervision to operate. It requires a driver." Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. That simple statement carried devastating implications. The German tank corps required highly trained mechanical specialists just to keep vehicles moving. The Americans had built machines for soldiers, not engineers. In the summer of 1944, with Allied forces now advancing through Normandy, the German Armaments Ministry received Kummersdorf's preliminary report. Its findings quietly circulated among industry officials. The conclusions were stark. Operational range. The M4A3 Sherman achieved an average operational range of approximately 480 to 500 kilometers on internal fuel, under normal road conditions. The Tiger I, with a full 540-litre tank, achieved between 110 and 130 kilometers in similar conditions. Maintenance interval. The Sherman could complete 3 to 4 operational days without significant mechanical service. The Tiger required routine inspection every 60 to 80 kilometers. Transmission reliability. The Sherman's 5-speed synchronized gearbox allowed easy gear changes at speed. The Tiger's unsynchronized Maybach-Olvar transmission demanded experienced operators to avoid tooth breakage and clutch wear. Cooling and lubrication systems. The Sherman's air filtration and oil circulation were adapted from pre-war civilian automotive standards. They tolerated dust, temperature variation and vibration far better than the precision-machined German systems. The report concluded, with uncharacteristic bluntness, American tank design demonstrates industrial maturity in mass-produced reliability. This aspect, more than armour or gunpowder, represents the primary advantage of the enemy's materiel. Albert Speer, Reich Minister for Armaments, read the report in late June of 1944. He underlined the phrase, industrial maturity. The phrase haunted him. In his post-war memoirs, he would recall, "We did not lack genius. We lacked pragmatism." The Americans had replaced craftsmanship with method. On the front lines, the contrast became impossible to ignore. As Allied forces advanced through France, reports from German panzer battalions became increasingly grim. Many Tiger and Panther units were immobilized not by combat, but by mechanical attrition. A typical example came from Panzerabteilung 502 during the retreat from Minsk in July of 1944. Of the 45 operational Tigers at the start of the month, 21 were lost to mechanical failures before a single engagement. Several were destroyed by their own crews after running out of fuel. Meanwhile, Allied tank units routinely covered 300 kilometers in operational redeployment without significant maintenance delays. In Normandy, American armored divisions reported average daily marches of 60 to 70 kilometers under combat conditions. For the German engineers studying the Kummersdorf data, these field reports confirmed what their tests had already shown. The Tiger's range, barely 120 kilometers on road, less than 80 off-road, was more than a technical statistic. It symbolized the collapsing strategic radius of the Reich itself. Every kilometer of lost mobility narrowed the front, shortened the reach of the once fearsome panzer divisions. Every immobilized Tiger became not a weapon of terror but a monument to industrial overreach. In late August of 1944, the Kummersdorf Testing Committee drafted a final internal memorandum. Its language was unusually candid for wartime Germany. The heavy tank, as presently designed, cannot be the foundation of operational doctrine. A vehicle of moderate armour, adequate armament, and mechanical endurance is more valuable in sustained operations than a superior weapon that fails to reach the battlefield. The memo never reached Hitler, but it reached the engineers who mattered, the men who would design Germany's final wartime projects, the E-series tanks, the simplified Panther II, and the projected standard Panzer. They all reflected, in varying degrees, the reluctant acceptance of a truth discovered too late, that reliability is not a luxury, it is strategy. In the months that followed, the war's tide swept beyond the point where such realizations could matter. German production collapsed under bombing. Fuel became so scarce that most tank crews were trained without ever driving a full-powered machine. And yet, within that crumbling edifice of industrial failure, a few engineers quietly acknowledged what the Sherman had taught them. One of them, captured in April of 1945 near Dessau, told his American interrogators, "You built tanks to drive. We built tanks to admire." That single sentence would later appear, almost verbatim, in post-war Allied technical intelligence summaries. It captured the essence of the conflict's most profound engineering irony. The Sherman, derided by many as mediocre, had outmarched, outlasted, and outserved the most feared tanks of the era, not by brilliance, but by balance. By the spring of 1945, Berlin lay in ruins. Kummersdorf, once the beating heart of German military innovation, was a shattered landscape of burned sheds and twisted wreckage. In the confusion of retreat, crates of technical reports were abandoned or destroyed, but a handful survived, retrieved weeks later by advancing U.S. Army ordnance officers. Among them lay the file-marked Versuchsträger 503, Sherman Evaluation, Captain William P. Harper of the U.S. 3rd Armored Technical Intelligence Unit opened that file inside the rubble-strewn laboratory. Between soot-stained pages, he found meticulous German notes written in an engineer's steady hand, endurance trials, lubrication data, temperature logs, and one blunt conclusion: the American tank is the most effective because it functions always. Harper smiled faintly. What had begun as a German study in superiority had ended as an unintentional compliment. In the immediate post-war years, these documents quietly shaped the reconstruction of German engineering. The men who had once designed weapons for the Reich now found themselves building for peace. In factories at Kassel, Augsburg, and Stuttgart, former tank designers applied lessons learned not from the Tiger, but from the Sherman. Karl-Heinz Bremer, once a Henschel engineer at Kummersdorf, later became a design consultant for Daimler-Benz. In a 1952 interview, he admitted, almost ruefully, "We pursued the idea of mechanical perfection at the expense of reliability. The Americans taught us that good enough if it works every time is better than perfect that breaks." That revelation became the quiet creed of post-war West German engineering. The new industrial philosophy favored modularity, ease of maintenance, and interchangeability principles that would later define the Volkswagen Beetle, the Mercedes Unimog, and, decades later, the Leopard 1 main battle tank. Across the Atlantic, the Allies studied German technical archives with equal interest. The Tiger and Panther fascinated ordnance officers and engineers alike, but for a different reason. They were marvels of craftsmanship undone by impracticality. 2. Army Ordnance Chief General Gladion M. Barnes summarized it in a 1946 report. "The German Army had the best tank in theory. We had the best tank in production. The post-war American tank lineage, M26 Pershing, M46 Patton, and eventually the M60 retained the core Sherman principle: standardization over specialization, interchangeable parts, accessible powertrains, generous tolerances, and industrial scalability became non-negotiable design values. Even the Soviets, who had won the land war with the rugged simplicity of the T-34, confirmed through captured German materials what they already believed: mobility, range, and repairability decide campaigns, not millimeters of armor plate. Within the reconstituted Bundeswehr of the 1,952nd, a new generation of officers studied both German and Allied wartime engineering reports. One of their first doctrinal memoranda declared, "Operational mobility begins in the factory." This was more than rhetoric. It represented the full circle of an idea first glimpsed in that muddy Brandenburg field in March 1944. A captured Sherman had shown the limits of pride and the power of practicality. The Leopard 1, introduced 2 decades later, embodied this lesson. It was light, mobile, reliable, and designed for long-range endurance on European roads. Its creators, some of whom had once tested the Sherman at Kummersdorf, knew they were building not another Tiger, but a philosophy of reliability reborn. History tends to glorify what dazzles: the massive guns, the thick armor, the feats of engineering that stretch the possible. But beneath those grand designs lies the quiet truth of war machines must serve men, not the other way around. The Sherman was never elegant. It rattled, it burned when hit, its guns sometimes felt underpowered. Yet it moved. It crossed continents. It arrived when and where it was needed. In war, presence is victory. The Tiger inspired awe. The Sherman delivered outcomes. In post-war Germany, That contrast became a metaphor for an entire national transformation, from obsession with mastery to respect for function. The country that once sought the flawless now sought the dependable. Factories that once built engines for conquest rebuilt engines for commerce, trains, and tractors. The same hands that once machined turret rings now milled crankshafts for trucks that would rebuild Europe. Decades later, in a small museum near Munster, a Sherman and a Tiger stand side by side. Visitors circle them in reverent silence. The Tiger gleams under spotlights, angular, intimidating, monumental. The Sherman, painted dull olive drab, looks almost humble. Yet when guides tell their stories, it is the Sherman that seems alive, the one that kept moving, that brought its crew home. One museum curator, a former Bundeswehr mechanic, gestures to both tanks and says softly, "The Tiger taught us how to design, the Sherman taught us why." And in that quiet space, surrounded by relics of fire and steel, the true legacy of those wartime engineers endures not in the perfection they chased, but in the reliability they finally learned to respect. The dawn mist hung over Kummersdorf like steam off a cooling engine. In the pale light of early June 1943, the German engineers who had spent weeks dissecting the American Sherman stood around the test yard in uneasy silence. What they had witnessed in the previous days had shaken their professional certainties. The Sherman had run more than 500 miles of continuous operation, through rutted dirt tracks, simulated battlefield obstacles, and extended endurance loops, without a single catastrophic failure. It consumed its fuel with mathematical predictability, its transmission ran cool under load, and its engine sounded no different after the final mile than it had at the first. One of the young officers, Oberleutnant Heinz Kruger, kept staring at the fuel logbook, as if the numbers might change. The Sherman's operational range, nearly 500 miles under field conditions, defied everything he had been taught about armoured mobility. His own Panzer VI Tiger, the pride of German engineering, could barely sustain 120 miles on a full load, and that only on roads. Off-road, its thirsty Maybach HL 230 engine guzzled through 2 gallons for every mile of advance. The American machine before him, squat and unpretentious, had accomplished in 1 week what a Tiger could not hope to do without an entire fuel column following behind. To the men of Kummersdorf, the Sherman no longer looked crude, it looked free. Inside the proving ground laboratory, sheets of paper covered the tables. Charts of consumption curves, crankshaft tolerances, and wear patterns crowded every inch. Oberingenieur Wilhelm Wolff, a veteran of the Daimler-Benz design office, dictated his findings to a stenographer. His tone was clinical, but his words carried the quiet gravity of disbelief. "The endurance of the American medium tank," he said, "is in no way comparable to our current armoured vehicles. The Americans have mastered the art of sustaining mechanical life under abuse." He paused, staring at the radial engine mounted on a test stand. "We build instruments," he murmured, almost to himself. "They build machines." The distinction would echo through the corridors of the Heereswaffenamt in Berlin within weeks. News of Kummersdorf's findings reached Albert Speer's office by courier. The Minister of Armaments read the summary in silence, then turned to his staff. The report's conclusions were damning. The Sherman's automotive reliability exceeded any German design tested to date. Its simplified transmission and generous tolerance for wear made it resilient to dirt, heat, and inexperienced handling. Its range rendered it independent of constant logistical support. Speer understood what this meant not just technically, but strategically. Germany's armoured arm had been built on a doctrine of engineering perfection. Every component of the Tiger was an achievement of precision machining, every bolt an expression of national pride. Yet those same virtues were now strangling the war effort. Each Tiger required 300,000 labour hours to produce and consumed fuel at a rate the Reich could no longer supply. The Kummersdorf report struck at the philosophical core of German industry. It was not that the Sherman was superior, it was that the Americans had defined superiority differently. By the summer of 1943, as the Wehrmacht prepared for Operation Citadel at Kursk, the logistical imbalance was reaching absurd proportions. A single Tiger battalion required more than 600 tons of fuel and lubricants just to reach its assembly area. Panzer IVs could limp forward when fuel convoys were delayed, but Tigers stalled where they stood. Crews often drained the tanks of damaged vehicles to keep a handful running. In contrast, the Red Army's Lend-Lease Shermans rolled hundreds of miles between refueling points, their twin diesel engines humming through the dust of the Ukrainian steppe. At Kummersdorf, engineers calculated that to give the Tiger the same range as a Sherman would require fuel tanks 5 times larger, impossible within its armour layout. When they presented in this arithmetic to the Waffenamt Directorate, an uncomfortable silence followed. Colonel Erich von Heller, head of automotive trials, broke it first. "Gentlemen, the Americans have solved the war of movement. We are still fighting the war of machines." Speer ordered a confidential conference at the Reich Chancellery. Present were representatives from Maybach, Henschel, and Krupp, along with technical officers from the Waffenamt. The minutes of that meeting, later recovered from Allied archives, read like a confession disguised as an engineering brief. Dr. Erwin Aders, chief designer of the Tiger, defended his creation with quiet pride. "The Tiger was built to dominate the battlefield," he said, "not to drive from Berlin to Munich without maintenance." "But what is the value of domination?" countered Wolf from Kummersdorf, "if the machine cannot reach the battle?" Speer intervened. "Gentlemen, we are not here to assign blame. We are here to learn why our enemy can build a tank in 8 days that runs 500 miles without failure, while we spend months constructing a machine that requires an army of mechanics to move 100. The room fell silent. The answer was written in every page of the American Industrial Playbook: standardization, interchangeability, and the acceptance of good enough in place of perfection. Meanwhile, across the Atlantic, American production lines were proving that philosophy correct every hour of every day. At the Detroit Tank Arsenal, the mile-long assembly line turned out a complete Sherman every 30 minutes. Engines arrived pre-tested, transmissions pre-fitted. A tank that broke down in the field was not repaired, it was replaced. Logistics became an extension of manufacturing, not its enemy. German officers, captured in Normandy the following year, would recall their astonishment at the sheer mobility of the American armoured divisions. Fuel drums stacked like towers along French roads, replacement engines airdropped to forward depots, mechanics trained to swap transmissions in hours rather than days. What the Germans had treated as a scarce jewel, the Americans treated as a commodity, and that made all the difference. Back in Germany, the Kummersdorf engineers continued their analysis. They examined the Sherman's lubricants and discovered high-detergent motor oil formulations that resisted carbon buildup far longer than standard Wehrmacht supplies. They measured the air filtering efficiency of the Donaldson cyclonic system and found it captured desert dust at twice the rate of their own paper filters. Even the electrical wiring astonished them. Standardized connectors, color-coded looms, weather-sealed junctions, simple features that cut maintenance time dramatically. These were not marvels of invention, they were marvels of discipline, industrial discipline. Wolf's final report to Berlin concluded bluntly, "The American tank is designed to be driven by men who are not mechanics. Ours are designed to be maintained by men who are." That single line was underlined twice in red pencil by Speer himself. By autumn of 1943, the Tiger's reputation as a battlefield terror was firmly established, but its mechanical shortcomings were no secret to those who built and operated it. The tank's drivetrain, straining under 57 tons of armour, required constant attention. Track links cracked under hard turns, final drives overheated, and transmissions failed after as little as 100 miles. Frontline maintenance companies often stripped functioning Tigers to keep others running, cannibalizing parts in field workshops that became graveyards of twisted steel. Reports from the Eastern Front grew increasingly desperate. At the beginning of Operation Citadel, the 505th Heavy Tank Battalion had deployed 45 Tigers. By the end of the first week, mechanical attrition had reduced that number by a third without a single enemy shell involved. One battalion commander wrote bitterly, "Our tanks are lions, but our roads are their cages." The comparison to the Sherman became unavoidable. Soviet crews operating Lend-Lease M4, a 2S, routinely completed cross-country marches exceeding 400 miles without refueling, their diesel engines delivering half again the fuel efficiency of German petrol engines. Even when knocked out, the Shermans were often repairable within a day. The Tiger, by contrast, demanded a logistical ecosystem that the collapsing Reich could no longer sustain. In the winter of 1944, as Allied bombers darkened the skies over Germany, Kummersdorf's engineers gathered their remaining data for safekeeping. The facility itself had become a target. American intelligence knew it as a site of secret weapons research. Yet, among the piles of rocket blueprints and jet turbine diagrams lay something far more subversive to the Nazi myth. A simple set of endurance charts showing the Sherman's range curve flattening gracefully after 500 miles, while the Tigers fell steeply before 120. When Soviet troops overran Kummersdorf in April 1945, they found those reports intact. Decades later, historians would marvel that among the debris of the Reich's scientific ambition, one of the most revealing documents was not a blueprint for a wonder weapon, but a maintenance log for an American tank. The cinematic irony of the story is inescapable. German propaganda had portrayed the Tiger as a symbol of indestructible power, its thick armour and 88mm gun, the embodiment of Aryan engineering. Yet the Tiger's greatest weakness was invisible to the cameras that filmed its triumphs, the narrow fuel gauge that determined its life expectancy. Every kilometre it travelled was a negotiation with scarcity. The Sherman, derided as Tommy's coffin by its enemies, survived not because it was invincible, but because it could keep moving. In modern warfare, movement is survival. When American troops advanced across France in the summer of 1944, their armoured columns stretched from the Normandy hedgerows to the Seine. German officers, reading intelligence reports, could hardly believe the distances covered. Major General Bayerlein of the Panzer Lehr Division later told interrogators, "The speed of your armoured forces was beyond our comprehension. We could not imagine machines that ran day and night without mechanical breakdowns." That disbelief had been born 2 years earlier on the quiet proving grounds south of Berlin, when the Sherman's engine refused to die. After the war, surviving German engineers were interrogated by Allied technical teams under Operation Paperclip and the British equivalent, Operation Surgeon. When asked what they had learned from studying Allied equipment, many gave predictable answers: praise for American manufacturing capacity, for British radar, for Soviet simplicity. But one testimony stood out. Ernst Knipkamp, a veteran of the Heereswaffenamt Design Bureau and one of the men who had inspected the Sherman at Kummersdorf, spoke candidly to his British interviewer in 1946. "We could not understand," he said, "how a tank so plain could fight a war so vast. We thought quality would win, but quality cannot march without fuel. You had quantity, but more than that you had distance. Your tanks could go farther than our armies." That sentence would appear years later in the British Ministry of Supply's internal report on German technology. It captured in one line the quiet revelation that had dawned too late for Germany to act upon. Industrial endurance, not mechanical brilliance, decides the outcome of a modern war. Cinematically, the closing image belongs not to the battlefield, but to the test yard at Kummersdorf. Imagine it, the Sherman's radial engine idling softly, exhaust vapour curling into the cold morning air. A handful of German engineers in grey overcoats stand by with clipboards, their faces unreadable. Behind them, the hulking silhouette of a Tiger looms, silent, its massive engine dormant for lack of fuel. The camera pans across the two machines, the embodiment of two philosophies. One built for excellence, so exacting it choked itself. The other built for service, so forgiving it could cross continents. The narration would fade over the low hum of the Sherman's engine. In the end, the war of machines was won not by power, nor by armour, but by endurance. The men who studied this captured tank understood, perhaps for the first time, that perfection is a luxury in a world that demands persistence. The Sherman's greatest weapon was not its gun, nor its armour, it was its ability to keep going when others stopped. The screen would fade to black, the faint rhythm of pistons continuing beyond sight, echoing through the ruins of a nation that had mistaken precision for strength. And somewhere in the archives of a lost war, the logbook still reads the same unassuming entry. Total distance, 500 miles. Engine performance, unchanged. When the smoke of 1945 cleared and the world's factories fell silent, engineers from every former combatant began tracing the war's mechanical autopsy. Among the spoils recovered by the Allies were hundreds of crates marked Kummersdorf. They contained no secret weapons, no jet prototypes, only logbooks, lubrication analyses, and wear pattern charts from a captured American Sherman tank. Yet those papers would echo far louder through the next generation of armoured design than any blueprint for a rocket or supertank. In the Allied technical archives at Versailles, British, American, and French engineers pored over the data with quiet fascination. The numbers confirmed what the battlefield had already shown. Reliability was the true multiplier of power. A tank that could drive 500 miles without a breakdown was worth 10 that could barely crawl 100. The concept of operational endurance became the hidden doctrine of post-war design. In 1946, at the Aberdeen Proving Ground in Maryland, U.S. Army ordnance officers laid out the lessons learned from both Europe and the Pacific. The M4 Sherman had proven reliable but lightly armoured. The Pershing, which arrived too late to alter the war's outcome, showed what heavier protection could offer, but at the cost of mobility and range. The question that haunted American designers was the same one that had confounded Kummersdorf. Could power and endurance coexist? The answer took shape in the late 1940s with the M26E3 and the subsequent M46 Patton. Its Continental AV1790 engine delivered more horsepower with improved fuel efficiency, using a cross-drive transmission concept directly inspired by wartime analysis of the Sherman's gear ratios. American engineers concluded that battlefield dominance was not achieved by maximum armor thickness, but by keeping a tank operational over successive campaigns. At Fort Knox, maintenance manuals for the new generation of tanks began with an unprecedented line: "Reliability is combat power." The phrase, coined by Colonel Gladion Barnes, became institutional doctrine. Every subsequent design, the M47, M48, and eventually the M60, carried that philosophy in its steel bones. The Sherman's endurance trials at Kummersdorf had, indirectly, rewritten the American approach to armoured warfare. Across the Atlantic, the British Tank Board faced its own reckoning. The Cromwell's failure and the wartime success of American vehicles under Lend-Lease forced a deep examination of British industrial methods. In 1947, the newly formed Fighting Vehicle Research and Development Establishment at Chobham conducted exhaustive trials comparing post-war prototypes with the American M26. The report's conclusion was unflinching. British tanks were over-engineered for short bursts of performance, while American designs achieved longevity through tolerance and simplicity. "A tank must not merely win a battle," one engineer wrote, "it must survive to fight the next day." The result of this introspection was the Centurion, first fielded in the late 1940s, a design that perfectly embodied the lesson of Kummersdorf. The Centurion sacrificed a few miles per hour of top speed for an engine that could cross entire countries without major servicing. Its modular components and wide-track suspension simplified field maintenance. By the Korean War, Centurions were running 2,000 miles between depot overhauls, an achievement that stunned even American observers. Behind its success was an invisible lineage, the ghost of a Sherman tested by German hands in Brandenburg. When West Germany was readmitted to the Western defense community in the early 1950s, its new engineers faced a paradoxical inheritance. The Tiger and Panther had made their nation famous, but infamous as well for extravagance, cost, and unreliability. The Bundeswehr's new Federal Office for Defense Technology and Procurement, staffed in part by former Kummersdorf veterans, drafted its first design philosophy document in 1955. Its title was dry but revolutionary: Grundsätze für Zuverlässigkeit, im Gefecht, Principles for Reliability in Combat. At the top of the first page was a simple statement: "The tank that moves is stronger than the tank that stops." Out of that philosophy emerged the Leopard 1, Developed by Porsche and Krauss-Maffei in the early 1960s, the Leopard rejected the heavy armour obsession that had defined the Tiger generation. It was lean, mobile, and built for rapid operational deployment across Western Europe. Its range exceeded 600 kilometres, almost the same figure that had shocked the engineers at Kummersdorf 2 decades earlier. When a retired Oberingenieur Wilhelm Wolff visited the Munich design office in 1963, he reportedly ran his hand along the Leopard's engine deck and said softly, "This is the tank we should have built in 1943. The Soviet Union, too, absorbed the lessons indirectly. Captured German documents circulated among Red Army design bureaus after the war. Soviet engineers had long favoured simplicity, but the endurance data from Kummersdorf validated their doctrine scientifically. The T-34's reputation for ruggedness had been born of necessity. Now it gained theoretical confirmation. The post-war T-54 and T-55 incorporated longer-life diesel engines, standardized gear systems, and simplified field servicing based on both Soviet and captured German studies. Soviet doctrine emphasized the march capability of armored forces, the ability to travel hundreds of kilometers under their own power before battle. It was a lesson the Germans had learned too late, and the Soviets would never forget. By the 1950s, the armies of the world were no longer merely designing tanks, they were designing ecosystems. Supply chains, maintenance depots, and standardized parts were treated as extensions of combat power. The Kummersdorf data had given engineers measurable proof that endurance could be engineered, not merely hoped for. In the United States, the Ordnance Department formalized a new metric, mean miles between failures, MMBF. It became the central performance measure for all armored vehicles. A tank's range was no longer judged by fuel capacity alone, but by the reliability of every component that consumed it. European manufacturers adopted similar standards under NATO coordination. The Western Alliance's Standardization Agreement 2456, issued in 1959, required all member nations to report endurance testing data in uniform formats, a bureaucratic descendant of that original 500-mile trial. Even the civilian industry felt the ripple. Automotive companies like Daimler-Benz and MAN, eager to rehabilitate their wartime reputations, adapted military reliability standards to post-war commercial vehicles. The same metallurgy that had once hardened Tiger transmission gears now ensured the longevity of peacetime trucks and buses that could cross Europe without overhaul. Perhaps the most profound legacy was psychological. The engineers who had once equated craftsmanship with national pride began to see restraint as a virtue. Perfection had cost Germany the war. Pragmatism had won it. Post-war German industry embraced failure tolerance, fault tolerance as a core design principle. Machines were to function despite imperfection. The new generation of engineers, raised amid ruin, learned that simplicity was not mediocrity but maturity. The Tiger, once a symbol of awe, came to represent a warning. Brilliance without endurance is futility. In 1967, a young historian at the Technical University of Berlin, Dr. Friedrich Lenz, unearthed surviving fragments of the original Kummersdorf report in the Soviet archives. His paper, Die Zuverlässigkeit des Feindes, The Reliability of the Enemy, sparked debate among military historians. Lenz argued that Kummersdorf marked the moment when German engineering confronted the limits of its own ideology. His thesis was controversial but influential. It reframed the study of technological history around philosophy rather than hardware. Lenz's work was later cited by NATO planners in the 1970s, when standardizing logistics for the joint main battle tank program that would produce both the Leopard 2 and the American M1 Abrams. Those tanks, though separated by nations and decades, shared one invisible ancestor, a captured Sherman tested in a German forest in 1943. By the dawn of the 21st century, armored warfare had evolved beyond anything those wartime engineers could have imagined. Yet the ghost of Kummersdorf remained in every engine test and endurance trial. The M1 Abrams, with its turbine power plant, can travel roughly the same range 500 kilometers as that wartime Sherman. The Leopard 2 achieves similar distances. Both are designed around maintenance accessibility, modular replacement, and sustained operations concepts first quantified on that proving ground south of Berlin. Military academies still teach the Kummersdorf paradox, the revelation that a simple, reliable system can outfight a complex, superior one when measured over time and terrain. It is taught not as nostalgia but as caution. In the quiet archives of the Bundeswehr's Technical Museum in Koblenz, there is a single surviving page from the Kummersdorf trials. The paper is yellowed, the type faint. It lists 3 columns: distance travelled, fuel consumed, and engine condition. At the bottom, underlined twice, is the entry that began a revolution in thought: total distance, 804 kilometres engine condition, unchanged. Visitors rarely notice it, overshadowed by the gleaming tanks nearby. But for those who know, that humble line marks the hinge of history, the moment engineers stopped worshipping perfection and began designing for endurance. The story of Kummersdorf did not end with the war. It began one. The quiet revelation of those German engineers that reliability is power became the foundation of every tank that followed. From the deserts of Kuwait to the steppes of Ukraine, armoured columns still move under the same unwritten law first learned in a ruined Germany. The machine that can keep going wins. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.